So we're going to be looking at arithmetic sequences and geometric sequences. We've been studying these in class for a while. Sequences are just lists of numbers. Right? This list of numbers is associated with an index. The index is almost always starting with 1 or sometimes with 0 and iterates through the counting numbers. We can define a sequence with either a recursive definition or a closed form equation. Are we trying to generate both of those? If we add a sequence together, this is called a series. When we see the letters N, J, I, K, or L, these are usually indices. Indices are always integers. Traditionally, mathematicians have used those letters for only integers. So here we have a recursive sequence that's arithmetic. On the left, you see the index, and on the right, you see the sequence itself. So we can use two different types of equations to define the sequence, the arithmetic sequence. The first one, I have the cursor over here, okay? So this says the nth A, which is in this column, could be the first A, the second A, the third A, and so on, is equal to the previous A. So if we were on A2, the previous A would be A1 plus a constant D. When we have a recursive definition, we have to have a starting point. A1 has to be given to us. We can also define the sequence with this closed form equation. This closed form equation can be used to generate any number in the sequence and does not require you to know the previous term. This is the more general description of the sequence. For this data set, I want you to take a minute or two and find both types of equation for this data set. So you'll need to get out some pencil and paper. The other topic we need to cover before we look at series will be the sigma summation notation. So this is the Greek letter capital sigma. Underneath the capital sigma is an index. The index beneath the sigma indicates the starting point of a series. So the first n will be given as k. K will walk through integers till it gets to I. It will walk through the integers in the positive direction. So for instance, if n starting point was -1 and the end point was 3, it would be -1, 0, 1, 2, and 3. Here, this is a function of n. It is some mathematical operation that will have the integer n in it. For example, it could be a 1 over n, or n to the third power. After the n changes, there will be an addition sign put in. So this sigma is summing. Okay, so we start at k and go to I. So an example, the most principal example of summing in a series would be just summing over n. So this would start with 1, and because the function is just n itself, we would be adding another integer for each series, for each number in the series. Now take a quick second and sum these. so you can evaluate this. Here we have another one, another function of n that we're summing over. So this one is 7 times n. We could have just written this as 7n, where n walks from 1 to 4. Now for each one of these, we change the n from 1 to 4 and then add. It turns out that we could have actually brought the 7 out in front of the sigma and summed from 1 to 4, but we'll go over properties of sigma addition later on. There's some other properties like that. So if you did this one, it would be 7 plus 14 plus 21 plus 28, whatever that is. Here we have a function that's a little bit more complicated. The function is 3 to the n, and we're iterating from 3 to the first, 3 to the second, 3 to the third. And if you evaluate this 3 to the first is 3. 3 squared is 3 times 3, which is 9. And 3 cubed is 3 times 3 times 3, which is 27. And you would add across those. Okay, this one looks a little daunting at first, but it's not a big deal. Here we're summing over 1/2 times n. And we start with n equals 1 and walks to 7. And now from properties of fractions, you know that if you're right or left multiplying a fraction by a number, you can put it in the numerator. So here we iterate through 1 over 2, 2 over 2, so on to 7 over 2. Okay, I did not simplify this so that you could see the structure of how this iterates through the integers and maintains this denominator. And like this one, it turns out we could have factored out the 1/2 and then summed over n. We would get the same result. Okay, I'm going to ask you to evaluate these sums. This is 1 over n, and this one's a little bit more complicated. It's 1 over 1 plus n. So on your paper, evaluate this series and this series. So here's another arithmetic sequence. Here's the data, here's the index, and here's the a of n values. Just for practice, I want you to produce the recursive form and the closed form for this arithmetic sequence. Okay, so I'm going to presume that you have a closed form equation for this sequence. So we also want to talk about series, so we're going to add across this sequence. Okay, before we start, you might just want to add these integers up. Okay, I'm going to show you what the closed form for this sequence will be. And then I'm going to show you the sum using that equation. So what this is saying is that if we add across our sum, if we add across all the index values from 1 to 5 of our closed form, we should get all of these added together. So I'm going to ask Maple to evaluate that to make sure we're right. Let's see here. Okay, so Maple says that this is 40. So if we add these numbers up, we got 15, 25, 15 plus 25 is 40. So summing arithmetic series is easy because there's an easy formula, and the formula is very intuitive because it's an average. So for a sequence, for a series with j terms, you can use this formula to find the sum of all the terms. You add the first term to the last term, and then you multiply that by the number of terms, and then divide that by 2. So, for this case, we would have we start with, well, the number of terms is 5. I'm going to divide that by 2. I'm going to multiply that by the first term, which was 2, plus our last term, which was 14. And Maple tells us, yes, so this is 40. So this is a handy equation to remember. Well, right now it's an expression. So this is posted on the wall, and I think you should commit it to memory, or ideally remember how it's derived, and just remember it that way. So we're basically done with arithmetic sequences and series, and next we're going to move on to geometric sequences and series. Okay, so now we're on to geometric sequences. Geometric sequence is different from an arithmetic sequence. We're not adding a constant number to a prior term. We're multiplying the prior term by a constant. This constant, we give the variable r, lowercase r. You can compute r by taking the quotient of 2 successive numbers in the sequence. This ratio is going to have the later term, usually, well, if the sequence is increasing, it's going to be the greater term in the numerator, and the prior term in the denominator. In fact, it's the opposite if the sequence is decreasing. Well, it's still the later number in the sequence that's in the numerator, and you'll understand this better in a minute. So we give this ratio, which is constant for any 2 successive terms in the sequence, the letter r, and the basic form of the geometric sequence we see right here. It's the later term is equal to the term just before it, that's right here, this is the term just before this one, times r. We can also write this like this because a times b equals b times a for numbers. This is the recursive form. In order to generate a number in the sequence from the recursive form, you have to know the prior number. Geometric sequences have a closed form if you know the ratio of the 2 successive numbers in the sequence, and the initial term, you can compute any term in the sequence. Okay, so we're going to look what happens to geometric sequences when we change r. Okay, so try to retain this equation right here. You might want to write it down. So here we're looking at a plot of a sequence. I've set the first term, a1, to 2. Now here we have the unusual case that r is 1. So the sequence would consist of multiplying 2 by 1 over and over, which would leave the sequence as a constant, which would be 2. So right now we're looking at 7 terms in the sequence. Now, if the r value goes up, then our geometric sequence increases. And now you can see the scale here is changing on the y-axis. We've moved to 7 terms, and we're already up to 15, and our r value is 1.4. Now you'll see if we increase the R value even more, this would be a more rapidly increasing sequence. Okay, so with 2, we've already gone up to 120 with just 7 terms. So what happens when R is less than 1 but greater than 0? So I'll put in 0.5. Okay, well all of a sudden we see that the geometric sequence is decreasing. We start at 2, it's divided in half. From 2 to 1, 1 is divided in half to 0.5. 0.5 is divided in half to 0.25, and so on. So this is dividing the previous number in half for each successive iteration. Okay, so we will look at what happens when this happens for many terms. Obviously, this is going to approach 0. So this is when the term is above 0 but less than 1. Now, right now, we're not going to consider the case of R being less than 0. We would find that then the sequence would alternate up and down. Those are important sequences. We will talk about those later. So that's your introduction to geometric sequences. Remember that it all depends on what the R value is. If the R value is greater than 1, if the R value is greater than 1, then the sequence is going upwards. If it's between 0 and 1, it's going towards 0, and it has more complicated behavior if it's negative. All right, next we're going to talk about summing over geometric sequences, so geometric series. Like we talked about arithmetic sequences, summing over them, they have a nice closed form, which I'll go back to. We learned that if you sum across an arithmetic sequence, you get this handy equation, and this one only works for arithmetic series where you're adding a constant to a prior number. We also have an equation for summing across a geometric sequence, and this looks like not a friendly equation, but what we have is the sum over the terms in the sequence. If we know the R value and our starting point, we can compute the sum of any geometric series. This equation here does not work when R equals 1. So I'll be asking if anybody can see why this is the case. Okay, so now we're going to look at some geometric sequences when we have the information about the successive terms. And we've just gone over the forms for the recursive and the closed form geometric sequences. I want you to study this data and find out what this recursive and the closed form equation will be. So you'll have to find R, that's in both of them, and you'll have to know what A1 is for the closed form equation. So I'll pause the projection, give you a minute to do that. Okay, presume that you've been able to do that now. And here is another sequence. Okay, we're focusing on this table here. This is another geometric sequence. I want you to compute both the recursive and the closed form expressions for this sequence. And I will pause the projection to allow you to do this. Okay, we're going to do one more sequence. This one's a little different. Here is our sequence, our last sequence. Try to compute the recursive and closed form expressions for this sequence. Okay, I'll presume that you have all three sequences and their expressions written down. Okay, if you haven't, then let me know. I will pause the projection and give you more time to do that. So we want to use this formula now for summing over these series. Now, if we take the three series we just computed the closed forms for, we can compute the sums. They're all from 1 to 5. We can compute the sums for all the terms in the sequence that we have using this formula. Now, A1 is easy. It's just the first A value in the sequence. And R is the ratio of two terms. Okay, so this is what the three equations are that you should have gotten for the closed form. Now what I'm asking you to do is to take this data from each of these and compute the sum over 5 terms. And in fact, you should be able to compute the sum over any terms. For this one, for the last one, I want you to compute the sum for 5 terms and then compute the sum for 100 terms. I think that you will find it interesting as to what's happening with the sum for the decreasing sequence.